Let's get this party started. So we have finished the first homework. Congratulations, everybody. The homeworks, as you've probably figured out, you do better if you start early. With the 1 a day auto grader, I know it's frustrating. It'll make you a better student because you'll actually start the homework earlier. You'll actually look at your code long and hard before you submit it because you only get to do it once a day. So it's a big commitment. You're not just going to throw things at it to see if it passes. You're going to actually think about it. I know you hate it. I'm totally comfortable with that. Now, we've rolled out a new homework, which is Bayes nets. And the first part is actually doing math. And we wanted to check your work, not just not the final number that you got. So we have a text file format so we can auto grade it. Sorry, I would love to go through each of your homeworks carefully with my red pen and look at it. I just can't scale that well. So we use an auto grader, and I recognize it's sort of a pain writing your mathematical formulas in type. Do it anyway. And that's due on Sunday. Okay. Let's get started. We are continuing our tour of thinking in the Bayesian way. And so this doesn't have a whole lot of new stuff in it, but it is interesting because we talk a little bit about the multivariate normal, the Gaussian distribution. And so let's get started. Fish. We're trying to develop a system that will guess what kind of fish you have caught based on its length and its width. So you're in a particular lake. The researchers before you have gone out and pulled out how many fish is that? 121 plus 154 plus 25. Oh yeah, here we go. 300 fish they have pulled from this lake, random fish. And some are trout, and some are bass, and some are catfish. And what they did is they weighed and measured each of them. They got the weight and the length of each fish. And you can see the different colors. The trout, for example, are red. The bass are green, and the catfish are blue. I'm sorry about the colorblind among you. You'll just have to believe there are green and blue dots there. Okay? So now you pull a fish out of the lake, and it is 16 centimeters long, and it weighs 2.1 kilograms. Based on just that, what do you believe about the breed of your fish? And so you're going to try and figure out the probability that it's a trout, given that the length and the width are what's given, or it's a bass, given that, or it's a catfish, given that. And those are the only 3 kinds of fish we have in our lake, so those should add up to be 1. All right? So what we're going to be doing is creating a Bayesian classifier. It's a machine learning tool, and this is based on the ideas that given the data you've got, you make up a probability of it being in one of these 3 different classes, and they should add up to be 1. So if we're doing this, we're going to use the definition of conditional probability. That is, the probability that it's a trout, given that it's got this length and this width, is the probability that it's a trout and it's got this length and it's got this width over the probability that a random fish pulled out of the lake has a length of 16 and a weight of 2.1. Oh, I was told that I'm not very visible when I point, so I'm talking about this formula here. And this thing under the denominator, the probability of seeing a fish with that length and the weight is just an average base that's weighted on the different kinds of fish. So we can figure out the probability it's a trout with this length and width, and the probability that it's a bass with this length and width, and it's a catfish with that length and width. And that summed all together is the probability that it's a fish that has that weight and length. Okay? All right. So how do we calculate this property, that the fish is a trout, its length is 16, and its width is 2.1? Well, the chain rule of probability says that it is the probability of seeing a length and a width of that, given that it's a trout, times the probability that it's a trout. Yeah? This is just the Bayes formula. Well, this is the chain rule for probability. Everybody's good with that? All right. So the priors, right away, before you make any measurements, you can get an idea of a randomly picked fish from the lake has certain probabilities based on these numbers up here in the corner. Right? If we picked random fish and we ended up with a whole bunch of bass, it means just picking a random fish, you're more likely to get a bass out. So we can use those numbers to create a prior. So we have the probability of a trout is 121 out of 300. Probability of a bass is 154 out of 300. Probability of a catfish is 25 out of 300. So this is our prior. This is given no evidence. What do we believe? And this is what we're going to update based on the likelihood of the data that we see. Okay? All right. So the prior is pretty straightforward. Now, the probability of seeing this weight and this length, turns out that you have learned enough about fish to know that the length of each breed is normally distributed, and the weight is also normally distributed. So I did this based on the color. You can see I put little dots down here along the bottom for each fish that I pulled out of the lake. That's the stuff we did the analysis on. Yes? Okay. So these are what we call the most likely estimators for a normal distribution. We can do the mean. Sorry. Yeah, I'm missing something there. This should say this should be the sum. This x should be here. My formatting got messed up. We're just going to sum up all the lengths and for a trout, and then we're going to divide by the number of trout. Sorry about that. You all know the formula for a sample mean, right? Go through all the samples, add them up, divide by the number of samples. And then the variance, once you've found the mean, you take the difference between each fish and its mean, you square that, and you sum it for all the fish, and that gives you the variance. All right? And I'm telling you that it just happens to be that fish are weights and lengths are normally distributed. So this is that definition of a bell curve. Have people seen this before? This is the norm. This is the formula for the probability distribution of a normal distribution. It's symmetric. See how the left side and the right side look the same? The very peak, that is the mean, that's mu. And then the width of this is determined by sigma squared. So we call the square root of sigma a standard deviation. And I marked that off. This is one standard deviation for that red curve. Yeah? So standard deviations they're in scale with what we think of as, well, I'll come back to that. So for all the fish, we can make these probability distributions. We have one for trout, we have one for the bass, we have one for the catfish. They look like this. So if I pull a catfish out, if I pull 1,000 catfish out of the lake, I expect when I plot their density that the weight will make a curve like this. If I plot their density, the length should make a curve like this. This is catfish. Everybody's comfortable with that? Yes. Okay. In Python, using JAX, you can very easily get the mean and variance of any list of numbers. So if I've got all the bass weights in a array, I just ask for the mean, I can get back the mean. If I have the weights in an array and ask for the variance, I can get back the variance. Of course, if I'm using the PDF call on the normal library, the scale is actually the standard deviation. So you always have to take the square root before you do this. This is something that we like to screw up a lot, is we'll do the variance and then we'll forget to take the square root before we use it as the standard deviation. As you might imagine, this has disastrous consequences. Yes? If they are anything other than one. All right. So this is where we have gotten the maximum likelihood estimates. This is sort of like if we think of machine learning as a training part and then using what we've trained on to do inference, this is the training part. We're looking at the data we've been given. Now we have this one fish that we want to do inference on. And so we can ask, what is the likelihood of seeing a weight of 21 kilograms, given that the bass weight mu is this number, and the standard deviation of bass weight is this, and I'll get back some number, right? This is 0.02. And I can do the likelihood of a bass being 16 centimeters long. And so here I'm asking, given this mu length and this standard deviation for length, what is the PDF? What is the probability density at 16? And I get back a likelihood. Okay, so far? We're getting there to where we can do this whole Bayesian thing. However, at this moment, you are very tempted to multiply those numbers together. You're saying, well, I've got the probability of this, I got the probability of that. What's the probability of both of them? I'm just going to multiply them together. But you're making a very big assumption at that point. You're making the assumption that they are independent. So the next line that you want to write is the joint likelihood is the likelihood for the weight times the likelihood of the length. But what you're saying is that the probability of the length and the width given it's a trout is equal to the probability of the length that it's given it's a trout and a weight given that it's a trout. Or what you're saying is the length and the width are conditionally independent given the species of the fish, which is a lie. Because of course, longer fish tend to be heavier. So there is a correlation between them. When you know the length of a fish, it actually tells you something about its weight. Okay? So if you do it anyway, if you say, I don't care that they're related, I just am going to multiply the two numbers together as if they aren't, you are doing what's called naive Bayes classification. And what makes it naive is that you have assumed that all the attributes are independent. And it makes the math a lot easier in a lot of cases. So in a lot of systems, this classifier will work really, really well, even if you make the naive Bayes assumption that they are all independent, even if it's a lie, even if they're not. You still actually, your classifier tends to work pretty good in most cases. So here's the steps to making a naive Bayes classifier. The first thing you do is you count your priors. So that you count the numbers of each class so that you can get the priors for them. And then you look at the things that were measured and you come up with parameters for those. Now, I said that the weight and the length of fish are normally distributed. And if you are working in other things, like we talked about the wait times, that's a Poisson. If you say, I saw 15 people in 2 hours, that's going to follow a Poisson distribution. And there's a parameter for that called lambda. And they go on and on. There's distributions for all sorts of common situations, and they have parameters. And so what you're going to do is figure out, this is probably follows sort of this distribution. And you're going to figure out the most likely value. In this case, it's mu and the variance sigma squared. In the case of Poisson, you'll be finding the most likely estimator for lambda. And anyway, you will go and estimate the parameters for each of these classes. Once again, Wikipedia has a wonderful page on every single one of these distributions, and you can get totally lost in each one of them. You're going to look up these, we're going to use the labeled data to find the parameters for each class and the priors. And then you're going into the inference step. That is, for each class, compute the probability of seeing the observed data. So we'll use the estimated parameter to compute the likelihood of each feature, and then we'll just multiply them together to get the joint. And then because it's the Bayes thing, we're going to multiply the joint likelihood by the prior to get that unnormalized posterior. We'll figure that out for all the different breeds of fish, the 3 different breeds of fish in this case, and we'll normalize it so they add to 1. And now we have really good probability of it being one fish versus the other. Okay? Questions on that? Follows from what we've done. It's the same idea. It's kind of neat that we're using these continuous parameters and ending up with a different classification based on it. All right. Now, independent versus correlated features. If you have features that are not correlated, you get these nice ellipses. It's tall or round. It can be flat, but you're not going to get diagonals. Diagonals, when they go up and to the right, that means the two properties are correlated. In this case, Long fish tend to be heavier. They're correlated. If they go from up and left down to the right, that means they're inversely correlated. So what would be life expectancy? As you get older, your life expectancy goes down. They are negatively correlated, okay? So you'll start to see these in these normal distributions. So once again, the length and the weight being independent, given that the breed, is a lie. There is a positive correlation in fish between their length and the weight, but the classifier will almost certainly work. What if we want to not lie? What if we want to tell the truth? What we could do is actually describe this sort of distribution. These circles, these are equal density lines. So when I think about the density, it's sort of coming out the screen at me. I have only this two-dimensional screen. If I had three, you would actually have a lump that was coming out at you. And these contour lines would be showing the borders between different densities as it got higher and higher. Everybody seen a topographical map? And they have the lines that represent a level walk. That's what these are. These lines are going around levels of density. Okay. Question in the back? I just saw a hand now. Okay. So if you have two variables and they're both normally distributed, and there might be some correlation between them, you need to go and use the multivariate normal distribution. And the multivariate distribution, because you're dealing with multiple things, X is now a vector. And so what you're going to do is you're going to add together all the vectors of a given class. So in this case, this vector would be the height, the width, and length. You'd add all those vectors together, you divide by n, and you get this mu vector, which is the vector in the middle. So in this diagram, this center point right there, that would be mu. It's not a number, it's actually a vector. And this is a two-dimensional vector, so it's pretty easy to see. But it'll be right there in the center. The tricky part is the sigma matrix. So when we had sigma squared, which gave us an idea of how wide that bell curve was, right? That was the standard deviation. With this matrix describes the shape of those ellipses. Are they correlated, inversely correlated? How steep are they? And the way we do it is you'll subtract the vector for the particular fish from the mean, and you'll take this is not the dot product, it's the opposite, right? It's the rows and columns and the rows and columns. So you would end up with if you have if this is a vector that has 7 components, this would be a 7 by 7 matrix. And it would be symmetric. So the sigma goes from being, sigma squared is a variance, it's a number. This is what we call the covariance matrix. And when you get all done, you can plot it out in 3D. It looks beautiful like this. Yes? Movie time. So I was thinking it'd be really nice if I could give you a movie that you could watch when you got all done with this, and it would explain the multivariate to you. And I found this amazing one. This professor at Princeton did all these great animations, and it's 6 minutes long, and it explains everything you could know. And I was like, they can watch it at home. And then I thought, no. I said, they need color commentary for this. I'll show the video, they can watch it, and I will stop it all the time in an annoying manner and fill in the color commentary. Yes?
Is there no standard deviation for multivariate Gaussian distributions?
There is nothing similar. We use the covariant matrix, and then there's a correlation matrix. So the covariance matrix and the correlation matrix are different expressions of the same thing. That would probably be the closest. Go. Come here.
Would the diagonal elements be I thought the
diagonal elements would be sigma squared. They would be the variance. Yeah, so you could take the square root of them, and that would be the standard deviation of each component of it. Yeah. Great. All right, let me show you the movie. I don't know how loud this is going to be. When everyone was in here, I tried it, and it sounded about the right volume. So that's kind of interesting, right? Because sums of random variables become normally distributed. So in particular, you have a bunch of genes for your height. You have things like how good your nutrition was, whether you smoked or not. They tend to be additive, and so the blend of them tends to create a bell curve in the population. So if you take men of a certain age, you would get a nice bell curve for height because it is sort of an additive thing. So what he's saying is this normal distribution does happen in nature, which makes it really interesting. There's essentially three things that make the normal distribution really interesting. And the first one is this one, that it actually does appear in nature pretty regularly. So if Chihuahuas have a normal distribution for their height, and Great Danes have a normal distribution for their height, and you want to know what is the distribution of Chihuahuas standing on top of Great Danes, the result of that will also have a normal distribution, and we can exactly compute what it would be based on the mean of the Great Dane and the Chihuahua and the variance of the Great Dane and the Chihuahua. Okay, cool. Right, so this is the second reason why we nerds love multivariate normal and normal distributions in general, is that it's closed under this. So we can very easily do all this math on them easy, easy, easy with matrices. Okay, so if we're mixing and matching the Poisson, the normal, and it gets really messy really fast, and we end up doing a lot of calculus. This makes it so we can just do simple algebra, and everything works great. So that's the other reason why a lot of the papers will say, assume that you've got n properties and they are all normally distributed with means of this and that. It's just very elegant and easy to work with. All right. Marginals. Remember what marginal is. That's where you forget about one of the properties of the object. So in the case of the fish, maybe for a bass, you have the weight and the length as a multivariate Gaussian. And now it's saying, just forget the length. What is the distribution of the weight? And what it's going to say is, you can just discard the stuff you don't care about.
What did they ask?
All right, a conditional distribution. So what he's saying now is you've got length and weight, and they are correlated. They're correlated multivariate Gaussian. And all of a sudden, you find out that you've been able to measure the fish. What can you know about its? You measured the length, about its weight. Well, it's going to turn out that its weight is also a normal distribution. The conditional, given the length is this, the weight is also going to follow a normal distribution. And of course, if the length is very long, the weight distribution is going to be kind of heavy. And if the length is very short, because they're positively correlated, the weight is going to be sort of low. It's going to have a low mean. So he's talking about if you know x3 through xn, how can you use that to guess the distribution of x1 and x2? And it's given this handy formula here. There's that thing behind it. He's going to talk about how you can generate numbers that follow a multivariate normal. It's fascinating, but nothing we need for this class, so I'm going to stop it right there. Questions so far? Yeah.
I'm just now taking linear algebra. How important was it that I understood how deeply that?
Nope, it's not that important at all. I just think it's fascinating. I don't think you're going to need it for this. You're not going to need it for this homework at all. Or the next one. But once again, it's pretty cool. Other questions? Yes.
When you said that you could marginalize away an infinite number of variables, does that mean that you could like assume a bunch of info about other variables given you have like whatever you know?
I'm going to punt on that one. Gaussian processes are fascinating, and they are far beyond what we can do today or even this semester. Okay. Yes.
Bunch of circles inside of each other, like why the circles and like what do they show in the same circle?
Yeah, so when he was showing all those circles and ellipses in concentrically, what those really were was that third dimension coming out at us, and those rings were level spaces on that surface. Is that okay? And the important thing, as you mentioned, is that this surface, when it comes out, the volume underneath it has to integrate to be 1. Other questions? All right. So this covariance matrix, it is symmetric. Why is it symmetric? Because if you have property I and property J, they have a covariance between them, and that appears both in the IJ and in the JI entries. So you end up with something symmetric. The diagonal elements, as Samir mentioned, will be the variance sigma squared for each property separately. And if they're correlated, the off elements will be positive. If they are negatively correlated, they will be negative. Now I'm showing you two dimensions because that's all I can fit on my screen, but these could be hundreds of dimensions deep. So this is nice to see, but keep track of if I had a dozen different properties of fish, some would be positively correlated and some would be negatively correlated with each other. Questions on that? Yeah.
Do closure properties still hold if like part of the distribution gets cut off? Like say if they
So this is actually really one of those things is that we love normal distributions, but normal distributions actually go infinitely in both directions. And so in particular, when we talk about length and weight, it's impossible for them to be negative. So we end up truncating these all the time. And so when we say something is normally distributed, it's a lie. It's always a lie if we're talking about properties that can never be negative. And it works out that a lot of times that's not a big deal. And this is the third reason why we love them. The third reason why we love them has to do with entropy. So I'm not going to spend a lot of time defining entropy, but you know from the way I say it, it's like chaos and unpredictability. And among all the distributions with a fixed mean and a fixed variance, and I could try all different distributions, the one that has the maximum entropy, the most chaos, is the Gaussian distribution. And so what happens is if I could prove it for the Gaussian distribution, it's usually true for anything that's got a similar idea that I can compute the mean and the variance. So no, the formulas don't work out perfectly if we truncate them. But it turns out that mathematically, if we prove it about the normal distribution, we actually have proved a whole lot of stuff. Is that okay? Yeah. All right. Here is the definition of the Gaussian distribution. And this part up here is about how far is x from mu. And it's a metric, and in some directions it's stretched, and in some directions it's a little bit compressed. And that's all handled by the inverse of the sigma matrix. And so when you when you multiply this, because the transpose is here, now you get these three together is just a number. And so this is the distance sort of idea from the mu, but stretched. And then pretty much all distributions have this idea of this is what gives it its shape. And this is what ensures that it integrates to 1. So this is boring. We don't care about that. We just need it there so that it integrates to 1. But this is the part that's actually we find really interesting and useful. So that's the definition of the probability distribution. And if you want to work with these multivariate distributions inside JAX, it's really straightforward because you can find the mean. So if this data is a whole list of, as an array of vectors, you can say which axis you're searching down. Here I assume that they were rows of data. I said go down the axis 0 and find the means. And that gets me mu, which would be a vector. And then I can ask also, take that data and find the covariance matrix for it. And this is the rows are different instances, not variables. So I say the row var is false, and that will give me the sigma matrix, just like that. So even though this is really messy and complicated, it's actually really, when you get down to the code, it's straightforward. And then if you want to compute the PDF, you just say, I've got this mean, I've got this sigma, here's x, which is some distance from mu. Give me the probability distribution for that, and it will return the likelihood that you're looking for. Cool? Yeah? Yeah. So we did naive Bayes, but in the case of multivariate normals, of multivariate Gaussians, it's kind of cool that we can actually do this without the naive assumption. This is one of the things that was in the movie, but I thought you might have missed it. So if we know some part of this Gaussian distribution, what is the probability density function of some other property? And so if we think of x as being a vector that's normally distributed around some mean with some covariance matrix, if we break that up into the two parts, the part that we want to know the distribution of and the part that we already know, well, then we can say, well, the mu has these two parts, sigma has these 4 sub-matrices, and then we can just do the calculation. Here is the mu for this conditional probability distribution, and here is the covariance matrix. It just follows this formula, and then you know the value. You're not going to use this in your homework either. I need to come up with an exercise that uses this, but I did want you to have it because I think it's really kind of a cool way. And these sorts of conditional probabilities, these are what we use in our Bayesian stuff. All right, so if we do it not naive, then we figure out the covariance matrix for each of these and the mean for the whole thing. And then we can use that and multiply it by the prior, and we get a really nice, my microphone on so people don't can hear. Get a really nice number that describes, without making the naive claim, what the posterior would be. Cool? Cool. All right. Now, there's another case that I want to talk about, and we don't love this one because it's not as pretty. We have this idea that the fish, right? We look at this picture of the fish data at the very beginning. We have this feeling that fish are dense here, right? These red ones, these trout are dense here, and the bass are dense here, and the catfish are kind of dense there. Yeah? And so what we're doing when we say this is a normal distribution with these properties is we're giving ourselves a really nice formula to talk about what are likely lengths and weights for a given breed of fish. But what if it doesn't, what if it's not pretty like that? What if it isn't at all normal? So let's say I've got something like this. This is just, I have this thing, I've got these measurements. How can I create some sense of the density from it? And there's this idea of kernel density estimators. And what you do is you put a little normal distribution over each one of these data points, and then you add them all together, and then you scale them so they integrate to one. And so if you do this, you get a nice curve like this. And you'll see this from time to time in people's research papers, right? They'll say we looked at the amount of time students looked at their homework. And they'll have a bunch of data points like this, but they want to get a nice, pretty smooth curve like this. This is how it's done. This is excuse me, a kernel density estimator. And it's super easy to do. I should have done this in JAX. We JAX scipy.stats, Gaussian KDE. You have an array holding a bunch of data. You say create a kernel density estimator for that. And then you can ask what is the density at any given location. This is just a one-dimensional one, but you could do it for higher dimensions as well. And it allows you to have these things that are multimodal, for example. Yeah.
So I thought if you add two normal variables, you have normal variables, that if you add.
If I add two normal variables, I get a normal density. But if I add these densities, I'm adding the PDFs. Yeah, I'm just adding the PDFs together. Yeah. So this is built into all these libraries, the Gaussian KDE, and you can put different little hats on the data points if you want, but this is the standard one. If you can set the width of the lump that you're putting on each data point, and if you make it too narrow, you get all sorts of little jaggies on this. And if you make it too wide, it gets too smooth and it's sort of rounding things off too much. This thing usually does a pretty good job of creating something that looks nice. But if you want to, you can actually explicitly say how wide you want it to be. Just wanted you to know about this. I am thinking about doing an example in a couple of weeks that uses this idea. I'll let you know if I actually get to it. So for the Bayesian classifiers, if you're not going to do naive, same idea. You count to get your priors. You come up with parameters that you need for the likelihood of the observed data. And then if you're doing naive Bayes, you use a univariate distribution for each feature, and then you multiply them together. If you're doing a parameterized true Bayes, you use like a multivariate distribution of some sort. In this case, it's probably, yeah. And we were just talking about the Gaussian version, and that's the one that's popular. Among all the multivariates, the one you bump into is the Gaussian multivariate. There are other ones, but not nearly as popular. And then if you want to do sort of parameterless true Bayes, you can use this kernel density estimator for the whole vector and use that instead. And then you can look up the likelihood of each of them, multiply it by the prior, and get the posterior, and then you normalize them, and that will be your classifier. So we can use these different properties together to update our beliefs, and we can use that to do classification. That's the punchline. Can I answer any questions about the idea of a Bayesian classifier? Yeah.
In the beginning, that naive Bayes is usually good enough. Exactly, what does that mean? Like, what is?
Naive Bayes is usually good enough. So, for example, the fish, right? All the fish have that same sort of smear in that direction. So if your fish is over here, it doesn't matter that you didn't take into account the very nice correlation. It's still well in the trout area. It's going to be a trout. If you're over here, it doesn't matter that you didn't keep it it's not exactly the right shape. It's going to be counted as a bass. And so usually the naive is good enough. If you do know that all your properties are normally distributed, then it's nice to do a full covariance matrix. But often you'll have one parameter that is normally distributed and one is following a Poisson distribution, and there's no way to create a multivariate that takes into account the correlation between them. Is that true? I can't think of any way to do it easily. So instead, we just do them separately and multiply them together. It's a very common situation. Okay. Other questions? All right, that is all I wanted to talk about tonight. thank you very much for coming, and I will see you on Thursday night.